And that's called a hyperbola. Hyperbola. Square. So what does it look like? You see, again, I can plot a point where it intersects the x-axis. I can take a here, and I can take negative a. And see, this is great because if you take a squared over a squared minus 0, this is 1. So this is like those points. But you cannot do the same as before, because if you substitute b instead of y, you get b squared over b squared, but you have a negative sign. So that's a key difference. Here you have plus. And actually, I would emphasize that here you have plus in both terms, and here you have minus. Because you have minus here, and so this is not equal to 1. It's equal to negative 1. Right? So those 2 points will not show up. And in fact, instead, what the curve will look like, it will look like this. Now, if you think that you're not familiar with this, you're mistaken. You are familiar, and because we have studied hyperbolas and hyperbolas, but usually we write hyperbolas by the equation y equals 1 over x, or maybe some coefficient, c over x. You see, what we used to call hyperbola before is given by this equation. It's a graph of the function 1 over x. Right? This is y equals 1 over x. The way I drew it, it looks like it's going to intersect the x-axis, but it's not, right? It's called this was called asymptotic. So there are 2 asymptotic lines to this graph, which are the coordinate axes. So this is a very familiar picture. So what's the connection between this picture and this picture? To understand this connection, let me talk about the special case when a and b are equal to 1. And the general case is very similar. When a and b are equal to 1, what this looks like is x squared minus y squared equals 1. And now here's the trick. I can write this as x minus y times x plus y. You see? And now I'm going to perform a kind of transformation that I talked about here. Namely, I will choose new coordinates, x prime, which is x minus y, and y prime, which is x plus y. And if you make this transformation, then this equation becomes x prime times y prime is equal to 1, which is the same as to say that y prime is 1 over x prime, which is our old equation for the hyperbola. So you see, at first glance, there is no connection whatsoever between this formula and this formula. But there is a connection, and you do realize this connection by using this transformation. Now, what does this transformation represent? This transformation actually represents rotation by 45 degrees. I'm simplifying things a little bit, because actually what it is not just rotation, but also it's a composition of the rotation by 45 degrees, and also multiplication of everything by a factor of square root of 2. So there is square root of 2 here, which is due to the fact that the cosine and sine of pi over 4 is 1 over square root of 2. But it's beside the point here. Let's not worry about this. It's a minor issue at the moment. What is important is that there is if I make a transformation like this, which is essentially rotation by 45 degrees, I bring this form to this form. Okay? And so that's the power of this kind of transformation, which allows you to relate equations which at first glance look very different. But in this particular case, we can actually use this transformation to take advantage of our knowledge from before, our knowledge of the hyperbola, to understand what this curve looks like in this case. Because what it looks like is just the old hyperbola rotated by 45 degrees. And if you rotate it by 45 degrees, that's exactly what you get. Rotate that picture is rotation of this picture by 45 degrees clockwise. Yes? Why is it clockwise? Because you have to, when you look at this formula, you have to explain why this rotation by 45 degrees and not by negative 45 degrees. So this is something, by the way, which is the subject of another mathematical course called Math 54. And I know some of you may have taken it or are planning to take it. So that's a course where this kind of stuff will be discussed in a very systematic way. Here we're not going to really dwell on it too much. I'm just giving you this as an example of the advantages of changes of coordinates, and also by way of explaining why this picture will appear if you want to study that equation. This is the explanation, because I have reduced the question of drawing this curve to the question of drawing this curve, which we already knew. Okay. So these are not the only possible cases. These are not the only possible scenarios for these quadratic curves. This is case 2. So there is another important case, which I'll call case 3. You see, the point is that up to now, in the left-hand side, I only had monomials of degree 2, x squared and y squared. I did not have monomials of degree 1. And the third case is the case when you do have monomial of degree 1. And that's the case when you have, which I'll write like this, y plus minus, in this case it doesn't matter, y plus x squared over a squared is equal to 0. And now that's also something which we know very well. That's a parabola. Because I actually wrote it in such a way that we can quickly recognize here the graph of the function minus x squared over a squared. So, and so that's this parabola. And also, if you want, you can add the other one where you would have y minus x squared over a squared equals 0. So that's the parabola. So this is red, and this will be yellow. That's this one, right? Because that's like y equals x squared over a squared. So two parabolas, one going upward, the other one going downward. In some sense, you can argue that these two equations are also equivalent, because you can get one equation from the other by flipping the sign of y. If you put negative y, it's the same as putting a minus sign here. So it becomes a subtle issue as to which coordinate changes do you allow. Do they have to preserve orientation or not? So I don't want to get into this. So if you want to think that there are two different cases, subcases here, parabola pointing upward and parabola pointing downward. So these are the generic quadratic surfaces, quadratic curves. I'm sorry, because we're on the plane, so these are quadratic curves. These are not all, of course, because if I really insist on the most general equation like this, I might as well take an equation in which there are no quadratic terms whatsoever, there are only linear terms. But if I do that, I go back to the case of degree 1, or degree 0 and 1 more precisely, and that's the case of a line. So I end up with a line. We have already discussed lines. So we're not losing any generality here by assuming that actually there are some non-trivial quadratic terms in the equation. Then you get one of those three cases. So all of this was by way of illustrating what we're up against now when we would like to understand a similar question in space, in R3 instead of R2. You see, in R2 it's easier to explain, there are three cases. But now we need to generalize it to the case of the three-dimensional space, which was our original problem. After all, right now we are dealing with R3 and we're trying to understand curves and surfaces in R3. This was a good digression though anyway, because it also gave us some useful information about curves on the plane. So in R3 we have to also include our third variable z squared, which will also give rise to the two cross terms like this, xz and yz, with some coefficients. So it will be some a, b, c, d, e, f, g and h and k, and then there will be some linear term. So there's a whole bunch of additional terms we have to include. However, as I already explained in the case of a plane, we want to transform this equation to the simplest possible form. And on the plane we get these three cases, and in space we're going to get the following cases, which I'm going to explain now. Okay. So again, transform to a nicer expression by using a different coordinate system. So that would be a kind of canonical form for a quadratic surface. So what are these canonical forms? They look very similar. They look very similar to what we had on the plane. The first few cases will be just like on the plane. On the left hand side, we're going to have a sum of squares or a combination of squares with different signs, plus or minus. So the first one is when all signs are plus. And it's very easy to understand what this is, just like the way we understood the ellipse. Because there's a special case which we understand very well. A special case when a is b and b and c are all equal to 1. Then we get the equation x squared plus y squared plus z squared equals 1. And that, of course, is a sphere of radius 1, which is centered at the origin. This is something we discussed before. So we already know sphere. So when I said we only know planes, it wasn't quite true. We already talked about spheres. So the sphere is a special case of this. But not only is a special case of this, but this is a case which will help us understand the general case, the way we were able to derive the ellipse from a circle. Because what we see is that now, by dividing these coordinates by a, b, and c, we have basically squished our sphere in a certain way in each of the three, or expanded it, if you will, depending on whether a, b, and c are greater than 1 or less than 1. We shrunk or expanded the sphere in each of the three directions. And so what you get is a kind of an egg, I don't know. Right? So that's a surface called an ellipsoid. You take the names for the quadratic curves and you change the SE at the end by SOID. No, not S. Anyway, you change the end by OID. That's how the terminology will be formed. So you have ellipsoid, hyperboloid, and paraboloid. Oh, by the way, I forgot to write that this is a parabola. And we'll get paraboloids in space. Okay. So what does it look like? It looks like this. It looks like a sphere. Well, to be able to draw this, you have to know how to draw a sphere to begin with, and then you kind of try to squish everything a little bit. Right? I don't know. That's my interpretation. This is a kind of contemporary art interpretation of an ellipsoid. Think of an egg, but the egg is not quite symmetrical usually. This has higher degree of symmetry. Okay, I will not try to make it better. You do it. You try to get a better picture. I think it's pretty clear. So what's next? Well, clearly, just by analogy with the two-dimensional case, we need to allow some of the signs to be negative. Okay, and then there are several options. You see, you've got yourself three signs in front of x squared, in front of y squared, in front of z squared, and so you can play with them any way you like. And so let's see what the results are. So you've got z squared now over c squared, and this is equal to 1. Now, the point is, the problem is, in two dimensions we only have two choices, plus or minus. You see, at first glance, it looks like two more choices because you could have minus plus or minus minus. But if you have minus plus, it's the same as this one, plus minus, if you just relabel the variables, x and y. You just relabel the variables. So it's not essentially new. That's number one. Number two, you cannot have minus minus, because minus x squared minus y squared, well, even if you divide by whatever, a squared and b squared, this is going to be negative always, or 0. It will never be equal to 1. And on the right-hand side, we purposely put 1. So we exclude that possibility that all of them are negative. So some of them have to be positive and some of them have to be negative. And what counts really is not which ones are which, but how many pluses and how many minuses. Here, all three are pluses. So the two remaining cases are when there are two pluses and one minus. So that's sort of like case 2.1. And then you have case 2.2, which is when you have one plus and two minuses. So that would be x squared over a squared plus minus. Sorry, so this is plus always, and it's minus, minus, and minus. So the question is, what do you get in those cases? And here, to analyze this, what is useful is to consider what's called sections. I will illustrate this notion in the case of an ellipsoid, even though my drawing is not that great, but I will try to explain it. So see, this is a surface which is like a sphere. You know what? Let's just look at a sphere. Maybe it's better, so that I can emphasize the most important aspect of a section without straining our eyes with an ellipsoid. So a sphere. So this is our coordinate system. Okay, and this is a sphere. Let's see if I can do it. So this is a circle, and this is like the equator, and this is the equator on the other side. It's more or less looks like a sphere. Okay, and that's a sphere. So now, what exactly is this equator? What exactly is the equator? I claim that the equator is nothing but what you get by intersecting the sphere with the xy plane. Remember, this is the xy plane. If you cut the sphere with the xy plane, what you'll get is precisely this equator. So the original equation was x squared plus y squared plus z squared equals 1. Now cut by the plane, by the xy plane, and the equation of the xy plane is z equals 0. Right? It's xy plane, so x and y can be arbitrary, but z is equal to 0. xy plane, but z is equal to 0. So if you cut by z equals 0, it simply means that you substitute z equals 0 into the equation, and so you end up with the equation x squared plus y squared equals 1. And that's a circle. And sure enough, we see that that's the equator which we are used to, which we knew was there to begin with. Now, the interesting point is, you can cut by other planes as well. We can cut by a plane, for example, z equals 1/2. So that's a plane which is parallel to the xy plane, but it sits a little bit above it at the height of 1/2. When we do that, we're going to cut a smaller circle, which is like if you think about this as the Earth, as the globe, this will be the parallel, one of the parallels, and so on. So that you can think of in fact, you can think of a sphere, of the entire sphere, as a collection of those sections. As you can cut by those, you can slice it by those planes, and each time you slice it, you end up with a circle. So if we didn't know what the sphere looked like, we could just imagine the collection of those slices and kind of put them together into. It's like if you don't know what the loaf of bread looks like, but you have a collection of the slices, you can kind of reconstruct in your mind what the bread must look like by kind of imagining those slices on top of each other, or side by side. So that's the idea of understanding surfaces. You have to realize that the surface is really a collection of curves. Those curves are obtained by slicing it by parallel planes. For example, z equals a constant, or instead of z equals a constant, you could slice it by x equals a constant, or y equals a constant. And that's the way we can analyze this picture. And each time we slice it, we're going to end up with a curve. And that curve will be one of those familiar curves which we have already discussed. So this is the way to understand what those surfaces look like. You try to see what the sections, what the slices are, and you recognize the slices simply because you have already understood what the curves look like. So, but I don't want to spend the whole hour explaining to you the details of this. I'll just give you the answer. I'll just draw you a picture, what it looks like, and then I will justify it by a similar argument. Okay. So the first one that I will draw will be the picture for the case 2.1, where you have 2 pluses and 1 minus. Okay. So what does it look like? I claim that it looks as follows. So this is a parabola which I had before. This is a parabola, and then I rotate this parabola around the z-axis. So it's going to look like this. Like this, like this, like this. Okay, you get the idea. And the reason is very simple. So of course I need the usual coordinate. I don't want to draw the coordinate system on top of it because it's already pretty messy, so I don't want to make it more messy. So I'll just draw it on the side. But you should think that, well, the z-axis is here. Let me just draw the z-axis. This is the z-axis. But so this is the x and y. It's the usual coordinate system. This is the z-axis. So how do I know that it's like this? Well, the point is, if you substitute some value of z, you see it's going to be minus z squared over c squared equals 1. But then I take it to the side, so I get 1 plus z squared over c squared. So I get some positive number, and I get the equation x squared divided by a squared plus y squared divided by b squared is equal to this. And I already know that that is an ellipse. So that means that my surface is going to be a collection of ellipses, which the smallest size will be when z is equal to 0, and then it sort of grows in size when z becomes large positive number or large negative number. So that's how I know. And finally, I can also look at I can slice it by a zx plane, and when I slice it by zx plane, that means I set y equals 0, and then I recognize hyperbola. So in this picture, you recognize 2 old pictures at the same time. You recognize 2 old pictures. One is an ellipse. That's an ellipse which you get by setting z equals 0, ellipse. But you also recognize in this picture a hyperbola, which you get by setting x is equal to 0. And that's a hyperbola. Well, it's not really a circle because at z equals 0, I'm going to get x squared over a squared plus y squared over b squared equals 1, right? And we have already decided that this is an ellipse. It's almost like a circle. And for the purposes of this diagram, of this picture, in the approximation which I use, it looks like almost like a circle. But we have to realize whenever I draw a circle, I include all possible ellipses as well, because they look so much alike. An ellipse and a hyperbola look very different, so then I would not mistake one for the other. I should not mistake one for the other. But an ellipse and a circle in first approximation is almost the same. So in my picture, I will not distinguish between them. So this is a surface which combines an ellipse and a hyperbola, and that's why it's called an elliptic hyperboloid. Elliptic hyperboloid. That's right. So I was going to keep it in suspense because then I was going to make another one and say what are we going to do because I have 2 different names, but now you spoil it, so it's okay. It has one sheet, which it's connected. This is just one piece, and so this already suggests that in the second case we're actually going to get more than one. So we're going to get in the second case we're going to get two pieces, 2 sheets. So in the second case I'll just draw the picture without explanation, but explanations are obtained in the same way. So in the second case you see I'm going to have two parabolas. Sorry, 2 hyperbolas.